Okay, so we're going to be looking more at our machinist device. This is in learning plan number 4. So to this point, what we've done is we've created our models. We've created our first draft drawings, looked at where things are fitting together to check if the tolerances were okay. And now what we're going to do is we're going to add some additional dimensioning, GD&T, to our prints to kind of complete them. We're not going to go crazy, but we're going to put them in some key areas that'll make some sense and to apply GD&T and kind of give us a nice little review of it as well. Additionally, today we'll be looking at the final assembly drawing as well. So I want to remind you of a couple things. First and foremost, let's look at the lecture videos here. Make sure that you're watching each one of these videos along the way. In each one of these, especially in the kickoff video and in the fits, there are documents and or PDFs that you need to fill out and hand in, okay? So you have to watch the full video to get all the information. So, so the first video here is the kickoff. This is going to be bill of material assembly planning sheet. You have to do that, hand it in exactly like we see it there. I do it with you in the video. If you try to print that off and just like randomly put things in, you're not going to get points. Okay, you have to watch the video top to bottom. Then you'll notice that the next one here is lecture 2. This is watching the full video as well. This is looking at creating the parts and the details. Okay, and this is first draft details, kind of getting them in their first draft sense with nominal values. Once you have those done, then you're going to move to fits and mating parts in this assembly. Again, these 2 videos you have to watch the entire time because I give you, and we work through the values for the fits. And then you're going to take those fits and now you're going to add them to the appropriate drawing. There are no guides for final draft drawings because from the videos, you have to get that information. And if you're missing this stuff and you're not putting the elements in place where they need to be, like the limit dimensions or the tolerances as shown on the videos, you don't get the points, okay? So learning activity is watching the videos to get this information. So there's 2 videos there. Now, today we're going to be adding another video on additional dimensioning, specifically GD&T, to add to these drawings, and then also looking at the assembly drawing. So it's going to be kind of our, if you would, final video in here, kind of wrapping things up and adding a couple more things before you hand in your final draft. Now, before I move into those elements, I want to look at the homework folder. The first Dropbox that you have is that bill of material and assembly planning sheet. Make sure you watch the video. Then the next 3 here, this is packet 1, 2, and 3. Instead of having all 10 drawings in one Dropbox, I put them into different packets. So the first packet is, 3 of our drawings, the next one is the next 3, and then the last one is going to be the final ones that you see here, okay? So, so each one of these packets has drawings in it that you're gonna be adding. And these are going to be the first draft drawings for each one of these elements, okay? Then down here, you're gonna notice that we have the next drop boxes for the vice fits, and it's that check sheet filled in. So it has all of the numbers. So that goes along with that tolerances and mating parts 2-part video series, if you would, okay? You have to watch both of those, and then you're gonna be handing that in. And then we have a final draft detailed drawings here, okay? And that's gonna be including the fits, which would be the any of the limit dimensions that are calculated with the tolerance and the fits from the check sheet up here. And those are identified in the videos, both videos. So make sure you watch them both top to bottom. And you're going to apply them here. Additionally, today we're going to be going over some GD&T that we're going to be adding to all of these, okay? So, so the GD&T and the fits have to be added here. All right, and then lastly, there's the final assembly drawing, and we'll be talking about that today as well, okay? So let's kind of get into things. Now, I am going to actually go underneath my camera here, and we're gonna start by looking at our assembly drawing, okay? And actually, I might as well go over the assembly drawing first, because as long as I have it up here. So number one, as we look at our assembly drawing here, you're going to notice there are two areas here where we have what we call stacked balloons, okay? So when you go in and you pull all these parts in, there's going to be two, if you would, little fasteners that you are not going to be adding in as separate pieces, but you do need to balloon them to identify them. So the first 10 items here are going to be assembled parts, and then it's going to balloon it for us automatically, okay? The last two items, the taper pin and the 1/4-20 UNC socket head cap screw, those are not going to be physical parts that we're going to pull into our assembly. Instead, we are going to add those in as stacked balloons. So number 12 is going to be our socket head cap screw that we're going to be attaching our plate on either side with, okay? So there's going to actually be 4 of those. And then there's going to be 2 of the taper pins that are going to hold the balls on either end of the rod that goes through our lead screw, okay? Now, the reason we're not pulling those in is because in Creo, we do not have the toolbox, okay? In SolidWorks, we have a toolbox option. In here, we don't have the standard toolbox. We would either have to draw it ourselves or we'd have to download it from somewhere. And instead of kind of going through that and adding that physical part in, it really just pictorially shows it there. Functionally, everything is lined up and everything is fine. So we're just going to add it as a stack, okay? And then what you'll do is you will add an item on the table, 2 items on the table, and fill it in on the bill of material, okay? So, so I just wanted to let you know that you do not need to add those 2 additional items there. You're gonna give them credit for being in the assembly, but physically, we're not gonna add them in as parts, and we'll just add them at the bottom of the table, and you're gonna add like 2 rows to the bill of material, okay? So, so that's how you'll handle that. And then in that drawing guides folder where we have all of the individuals, at the very bottom, you're going to see this this page for the assembly. So when you create it, you are going to be putting a section through here so that we can see these internal pieces, all right, so that we can balloon to those. So I just want to make sure that you know what the requirements are here for the assembly. Otherwise, it's really straightforward, okay? There's 2 sections. There's a section here and a section here, and that way we can see everything that we need to get at get at all the parts, so that nothing is hidden, if you would, or we can't view something. Make sure you take off hidden lines, because otherwise it gets pretty cluttered. And then yeah, then I think everything should be all set for you. Pretty straightforward. Any questions assembly drawing wise at all? Okay. All right. So that's your assembly. Let's look at the GD&T on individual parts that are going to be, you know, kind of make things up. So what I've done is I've targeted some parts. Now, we're not going to put GD&T on each and everything. Now, do you have to, or do you, I mean, you always want to kind of consider it, all right? But I also want to make sure that you understand that, especially form tolerances, we're only going to add them when it's a refinement on what the assembly is already giving us, or the dimensions are already giving us. So, so there are some things that we're going to be adding. Position tolerance is one that you always want to look at, because it's the right way to dimension locational or location for features of size. So we're going to look at that and look at some areas where we're going to apply that, and then also some orientation tolerances like perpendicularity, parallelism, and such. So the first part I want to look at is going to be our base, okay? So the things that I identified here that would be appropriate for this is, first and foremost, looking at the feet. So when this is sitting down, for instance, we want those feet to be on the same plane, okay? So we want this not only to be flat, if you would, but we want them to be on the same plane. So what that means to us is we need to then look at not flatness, because remember, flatness is going to be flat on one continuous surface. And we actually have, you know, two continuous surfaces here, all right? So they're separated by this little, distance here. So if we would put flatness, for instance, on one side, it would only be flat on that one area. And if we would put another one on the other side, they could be like this, all right? So we want them all in the same plane. So that means that we have to use profile for this, and profile of a surface, okay? So surface profile. And we can add it now. I know there's not a ton of room here, so you remember we have a couple ways that we can call these types of things out. So you can either attach it, to the surface, or what I would do, I would simply point at the surface and then create my feature control frame, okay? And I'm gonna sketch them on here just because I think it's a little faster than having it up in Creo. So I'm gonna sketch this on here, but you would be adding the official callouts. So this would be surface profile. It's going to be the closed half circle on the bottom. And right now, if we look here, our tolerance for machined surfaces is going to be, plus or minus 20 thousandths right now, because this is a 2-place decimal to the bottom. So what we'll do is we'll add, we're going to say, okay, we need that to be a refinement of more than 40 thousandths. So we're going to say, okay, how about we'll put a flatness on there. We'll make it nice and flat, all coplanar, and that's going to be something less than 40 thousandths. I'm going to say 10 thousandths. Okay, we don't want to go crazy. This is a vise. It's not something that's super duper critical, right? So if we make it super duper flat, you're also going to take more time to make that flat, or flat and on the same surface, coplanar. But you're also then going to induce time and money. So we want to be reasonable. And so this would be flatness or surface profile of 10 thousandths. Now, datums. As we look at it right here, we just want these to be flat to one another. We don't need it to be parallel to anything else or anything like that. So what we're going to do is we're just going to leave it at that. We're just going to add, and what this is it's basically saying, I want these to be flat to one another, okay? So this is going to be surface profile, and then the only other thing we need to do is we need to do 2 surfaces underneath, okay? Sorry, mine kind of ran in there. So, but with CAD, and you'll be able to move things around, you'll need to get it in there. So 2 surfaces, because we want it on both of these, okay? We want those to be coplanar, and that's all we need to do, all right, with the profile. What that does for us is we say qualifies that surface, okay? Because then if we need to use it additionally for anything, then we can. It becomes kind of like a datum. We're going to finish that off really nicely so that it sits nice and it doesn't rock or anything, okay? So that's the profile. Now, once we have this profile here on the bottom and we have that bottom surface, the feet nice and flat, then the next thing to consider really is, as we look here, this cutout, right? This cutout could be perpendicular and parallel to one another. So what we could do is we could add to one of those side surfaces, and right now it doesn't really look like one is more important than the other. But what we could do is we could add, for instance, on the outside here, and you can't do it on the dimension because you have to come off the surface, and that's where the challenge will probably be dimensioning wise. So I'm going to kind of extend, actually, you know what we could do? We could point, I do it where the dimension is. This is the inner, this is the outer. So you might have to change things around here a little bit, but what I'm going to do is I'm going to say, okay, I'm going to go along here and I'm going to kind of blow this up. This is going to be a perpendicularity tolerance, and we want that to be perpendicular to the bottom surface. So once this is a profile tolerance on it, we are going to make it a datum. All right, now see here that I got to move this. This needs to be 2 surfaces. This is the beauty of CAD, because it's easier to move, but then this is going to have to become a datum, okay? Because I want this surface right here to be perpendicular to datum A, all right? So my feature control frame here is going to be perpendicularity. Now, what do I need that value to be? As we look at the dimensions that are given here, you'll notice that they're 3-place decimals. So that means they're plus or minus 5 thousandths total. So the total tolerance between the plus and minus 5 is going to be 10. So we need something less than 10 thousandths. So we're going to go 0.005. We'll say 5 thousandths, and we're going to be perpendicular to datum A. All right, that's going to be that side right here is going to be perpendicular to the bottom. Now for the other side, we could say that should be perpendicular as well, or because we know that it needs to, be pretty critical between there, we're going to call out this side over here, the opposite side. And again, not a lot of room there, but we want that to be parallel to the other side, okay? So once this is perpendicular, this is going to become datum B, okay? And then this we're going to have, that's going to be 5 thousandths perpendicular now to datum B. And then that way, both of them will be perpendicular and parallel to one another, okay? So that would be appropriate to add to those two surfaces. Additionally, and I'm not going to add them in there, but you would want to do it on these two surfaces in the inside here as well. Okay, in the inside here as well. So you would want to add the perpendicularity and then the parallelism to the other side. The challenge will be getting it in there, okay? You could, if you wanted to, if there's more room over here, if you can find that there's more room over here, you could do that over there as well, okay? You always want to try to keep your dimensioning in the same view, anything for GD&T and size. So best to try to get it in here, but if you can't, you can default over here as well. So that's going to be looking at that cutout. Those would be appropriate for the cutout. Another parallelism that we'd want to do is going to be this rail right here, okay? Because when we look at the assembly, this is going to be riding on that rail back and forth, right? So it's a good idea then to have that running parallel to our bottom. Now that surface right there is called out right here, right? The dimension for it. So and this is going to be a surface call out, we could do, a pointing at, and then we could call that out parallel to, and that's going to be, I would do the 5 thousandths again, to datum A, okay? Now, the last thing on here that would be a consideration is going to be position tolerancing, okay? Position tolerancing is whenever we have a feature of size, like tapped holes or a through hole, we want to position that, okay? So in the case of the 1/4-20 holes right here on our base over here, and that's where the that plate is going to be mounted, right? We want to add a positional tolerance for those holes. Now we're going to add it where the holes are called out. So the holes are called out right here, all right? Now again, I don't have enough room and to draw small enough, so we would add underneath here a feature control frame, okay? But I'm going to kind of blow it up over here, all right? So our feature control frame is going to be for position. And now we need to figure out the number that's going to go in here. Now, if you remember from GD&T, we had two different types of, we call them two different types of positional tolerances. There was fixed and there was floating, right? So a fixed fastener situation is where we have a through hole or a clearance hole in one, and then it's going to thread into the other. That's the situation we have here. So my tolerance, okay, my diameter here is going to be a tolerance here. All right. Now, because it's a clearance hole fit, we're going to add the maximum material condition, and then we're going to have some datums where we're locating from. Okay. So we'll kind of plan that out in just a bit. Now, tolerance-wise, that tolerance, to calculate that tolerance, P is going to be equal to H minus F divided by 2. Hopefully that's kind of coming back. H is going to be the maximum material condition of the hole. Now, the hole that fits on there is with the plate. Plate. You see right here, okay? This is going to be your jaw plate. So this is the hole. The through, we want to go on the through hole. So here's my through hole. My through hole has a plus or minus 5 thousandths on it because it defaults to the title block, okay? So that means that my largest hole size is 0.286, and my smallest hole size is 0.276, right? My maximum material condition for an internal feature is going to be its smallest size. So the maximum material condition for that hole is 0.276. That is going to be the H value here, 0.276, okay? Minus the maximum material condition of the fastener. The fastener size is going to match whatever our tap size is here, right? So the tap size is 1/4 20. So the maximum material condition of a fastener will always be its nominal size, so 0.25 divided by 2. So it looks like we've got 26 thousandths on top divided by 2. My tolerance is going to be a diameter of 13 thousandths. Okay, now that tolerance is going to go up in here. Okay, 0.013. Now, since we are locating it with a positional tolerance here, that means that the very same positional tolerance is going to go here. This is going to be 13 thousandths, same thing. All right, maximum material condition, and then we'll add datums when we get over here. Okay, it'll be the next place that we go. So we have our number. We calculated it based on the fit, maximum material condition, because it's a clearance hole. And now here are my datums. Okay, so we've got to look. Well, where is our dimensioning coming from? Okay, so you'll notice that this is up from the bottom. Then you'll also notice that it's chain dimension to the very bottom of the base. That's where we want to go to. Okay, at the bottom of the base. So we're going to use datum A as our primary because we're locating up. Okay. Actually, no, that's going to be one of our locators. It's going to be our secondary. Okay. Our primary datum is going to be the main mating surface, which is this surface right here. Okay. So that surface right there, we are going to call, we did an A, we did a B, we're going to call that datum C. You have to scooch it in here. You might have to move something, right? You have to have a landing on here. Datum, we're going to call it C, okay? So datum C is going to be our primary because that's the main mating surface of these two parts. Then datum A, it's coming up from the bottom. And then when we look at its location, you're going to notice that it's coming from this corner. So that means that this also has to be called out as a datum, okay? Because that's where it's being located from. And we'll call that datum D just because that's the next letter in the alphabet. So it's CAD for this. Now, before we move from this one, the next thing that we need to do is we need to add in our basic dimensions. So any dimensions that are locating this, and the 2 or 3 dimensions, it's going to be up from the bottom. This is going to be basic. This is going to be basic. And this dimension right here is going to be basic, as well as the dimension in between, because that's its spacing. So the 1.5, the 0.625, the 1, and then the 2 chain dimensions back to our datum right here. Okay? All right. And then this is going to be our feature control frame that we put by the 2 1/4 20 taps. So on this drawing, we've got profile on the bottom, becomes a datum. We've got perpendicularity of one of the sides here, it becomes a datum. Parallelism to the other side for that datum. Then we want to do that same scheme on the width of the cutout up here. Parallelism of the track to the bottom, and then position for the 2 holes. All right. Now, let's go back to that jaw plate. All right, we started the jaw plate. We're like, yep, we're going to position that. We know our number because it matches up with what we just calculated, but now we need datums here. So our first datum, remember, is always going to be the main mating surface. So the main mating surface that's going to mate with the base is going to be this surface right here. So we're going to call this out. Now, this isn't a super critical part. So sometimes we'll say we want to qualify that first, but in this case, we're just going to say it's datum A. All right, it can come in, as whatever the surface finish is. So we're going to call that datum A. That's going to be our primary datum, main mating surface. And then we have to look at our dimensioning scheme. Where are we dimensioning from? It looks like we're from the bottom and then over from this corner. So this is our 0, 0, if you would. So that means that this bottom surface right here would be a datum. And this side surface is going to be my other datum. And again, this isn't super critical as far as like surface finishes, because again, we're machinist vice. So now, datum-wise, which one's secondary, which one is tertiary? Well, secondary, we usually, unless there's any other reason, we look at the longest side, because we're going to be putting, 2 supports on here to stabilize it. So we're going to call this B as our secondary, our longer of the 2, and C is going to be the tertiary, the shorter of the 2. Okay. And then lastly, we're going to put our basic dimensions. So coming from that corner, the 1 inch is going to be basic, 0.625, and the 1.5. And that's all we need on this one. Okay, just positioning those holes.
Kelly?
Yes.
Question on the base. So that 1 inch dimension on your far right view,
Yes.
I think that one's supposed to be coming from the start of the sectioned part right there.
No, that's actually to this surface here. There's one on this side. Is that what you mean?
So the distance from the 1 inch dimension to the holes.
Yes.
Like looking at the pictorial, it looks like it comes from that middle surface.
Right.
And right now,
and that chains us, because we need to get back to the bottom here, right? And that's the one that's related from here to here. So those 2 have to be basic to get our position, our location for those 2 holes.
right.
Because we don't have a direct dimension right
now. So do you know what I'm saying? Like that 1 inch dimension, it's not, I don't think it's dimensioned to the right place. Like if you look back on the pictorial of the base.
Oh, I don't have that printed out. Oh, so you don't think this is the right, so you don't think that's the right dimension. You think 1 inch should go to here?
Yeah, yep, that's the way it's showed in the pictorial.
Oh. I don't have it. Oh, you have it. Look at.
I just started working on it, so.
You're right, Joe. Look at that. You're right. So that dimension would actually be, that's an 1/8 inch up. So this would actually be 7/8 of an inch, is what you're saying. The
Okay,
so value. Yep. So that should be, it looks like 0.875, right?
Right. Okay.
Gotcha. I must have, and because it's an 1/8 of an inch up, so then the distance between here and here would be 0.875. You're correct. I have to adjust that on my model.
Okay. Yeah, I just wanted to make sure that they
So
should stay in a chain though. Like I shouldn't keep it a 1 inch dimension, but I should change it to a 0.875.
Sorry about that. Yeah.
Okay.
My fault. But it would be 0.7 from that surface, and then yes, it would be physically 1 inch between here and here.
Okay, but I wouldn't do that 1 inch dimension there to there.
You know what? It could be either or, honestly.
But then the basic dimensions wouldn't work then, right? Because it wouldn't chain back.
Then we'd have to use this one over here. If you went from here, the 1 inch.
Oh,
and
yeah.
then down. So, like I said, it's either one or the other. It's totally up to you. If you want to do the 7/8, then go on this side. If you want to do the 1 inch, then you have to include this one.
Okay.
Oh, yeah, either one. Because again, it's machinist vice. Honestly, not that critical. But that's, I mean, yeah. Thank you for pointing that out.
Sure.
Okay. Then, and again, I don't want to get super duper crazy with the GD&T. This is a great place to introduce it in the next semester in our design problems class. We are going to be going deeper again. So, so this is a great place to just kind of bring some of these things back up. And because it's a machinist vice, I don't want to give the interpretation that GD&T is only when we have things that are critical, but we also use it when we need a refinement on what the dimensions offer us, okay? And when we need some different, you know, like especially with position, it gives us more freedom for actually opening up the tolerance as opposed to being more restrictive. So position, we always want to consider, especially when we have these holes that are holding something on that's a clearance fit. So, you know, the tapped holes here with the holes in that jaw plate, that's perfect application for position tolerance. But you'll notice that we're not adding perpendicularities and parallelisms to every surface. You know what I'm saying? You don't have to. And you always want to look at your application to see if it warrants it. A machinist vice is relatively crude, okay? Its job is to just, you know, clamp something together, right? And so if this runs smooth like butter, or if it does have some friction and you have to push on it, in the end, we're just holding something together so it doesn't move. You know what I mean? So, so we don't have to be super critical, because as we're putting more and more restrictions, and especially when we're looking at form and orientation tolerances, what's happening is it's going to take more time to get there. It is going to increase the cost. But when we look at things like position, knowing when we have maximum material condition, now all of a sudden we're opening up the tolerances. So that's where understanding how the tolerances act is really important, because here I opened up tolerances for us. Here I'm functionally want everything to be on the same plane, right? And so that it doesn't rock when it's sitting. And it's not a crazy tolerance here. I have 10,000s. That's not super critical. If I start going into 5s and 2s and 1,000s, that's critical. Here, this is going to be controlling how that moves in and out. And so I want to be sure that that does move smoothly. I don't want it to jam up anywhere. So again, 5,000s, which is going to refine on the existing tolerance that's there, is appropriate. Okay? All right. Then the next one, and really I think that I'm kind of looking here. This is like the last one that I really wanted to do. Again, not going crazy with things, but just kind of, you know, looking at some relationships here as it goes together. We would want to do the position tolerances here on those tapped holes again. Now, this is the other side where the jaw plate is added to. So because it's the same jaw plate and it's the same size fasteners, we're going to use that diameter of 13,000ths maximum material condition, and then we'll just devise our scheme for our datums. So we have to look, where is this being dimensioned from? And so you'll notice here that we're dimensioning from the bottom here up for that location of that hole. That does need to be 1 inch, does it? Because I'm looking at it where it's riding on. So yeah, that needs to be 1 inch. It's here. It's appropriate here. And then you'll notice that we're coming from this edge over here. So this is going to be a basic dimension. This is, and this is, and then that's how we're going to do our datums. Now, our main mating surface is going to be right here again. So yeah, I didn't plan this very well. So this is going to be our datum. We'll call it A. We'll kind of go up with our datum scheme here. That's going to be datum A. Datum B is going to be this surface here, because that's the dimension up, and then datum C, not in line, got to be off. Remember, don't put your datums in line with any dimensions, otherwise it's going to assume the center plane of something, and that's going to be C. This will be A, B, C. Okay? Another one you could do profile, where it sits on the rails here, where you would have a profile tolerance. Actually, that's probably what we got to do first. So we would put a profile tolerance here, surface profile, and we used on the base, we used 10 thousandths. We can use that same number, 0.010, okay? Then it becomes datum B. And that way it's going to keep these two on the same plane. So when it goes across those rails, it's gonna sit nicely. And then the other one that we could add would maybe be perpendicularity of this surface to those rails as well. So we could say, and I'm gonna actually put it on this side, we could say perpendicularity, maybe 5 thousandths, because that's a 3-place decimal. And this would be perpendicular to datum B. And then after it's perpendicular, it would actually become, let's see, base here, datum A. So our datum A would be attached then here. So that surface would be perpendicular down to the rails. It becomes datum A. And then it's used here to position those holes. Does that make sense?
Yep.
Yeah. And that's as much GD&T, especially on, like I said, a machinist vise that I would go to.
Okay.
All right. So really, GD&T would be on our base, the jaw plate, and the sliding jaw. Now, if you would recognize you want to add some along the way, I'm open to that. But let's start there with kind of the minimum requirements for the GD&T. Okay. All right. So to your final drafts then, adding the GD&T that we've identified here in this video, then you would be ready for your final draft by implementing both this and the tolerances and fits video information, okay? All right, any questions, Joe? And if something comes up like as you're working, certainly can look at those individually too, because we'll still be meeting tomorrow too.
Okay. Yeah, I know we only added a little bit of the GD&T, but I was just looking at the mounting holes on the base. I don't know, do you think those would normally need it?
Well, I will say this, on the mounting base, these holes are going to be quite generous based on the fastener size. So for instance, I would anticipate that a 1/4 20 socketed cap screw would go through there. So we are looking at about 1/8 of an inch clearance.
Oh.
So it's already quite generous with the size of the hole that's there.
Okay.
Yeah,
I guess if you are installing a vise, you're just gonna drill the holes where they end up. So.
Right. So it's not, and again, I don't want to make it sound like, oh, position tolerance makes it more critical, because in most cases it doesn't. But remember, this is again, these are really large holes. Almost, and in many cases, you may even see slots for them. So you've got room to play with.
Yep.
Yeah, but if you know what, Joe, if you wanted to add them, go ahead. You can do that very same process here. Your fastener will be 1/4 of an inch. Whatever the size is here, you can figure out what the smallest hole size would be, and you're going to have then a larger, diameter here.
Okay. I got nothing else then.
Okay. All right. Well, that's a great start. And so tomorrow we'll meet, and if you do have additional questions, or if I think of anything else, I'll add it. Okay.
Sounds good.
All right. Okay. Cool. Well then, yeah, let me know if anything comes up as you're working. And yeah, that's it. That's all that I got for today.
All right. Thank you.
You're welcome.
Have a good one.
You too. Bye.
Bye.